quick. The point of this is this. Deactivators, not only do they make the ring less nucleophilic, they also, do you think they're going to stabilize any sigma complex?
No.
No. Right? There's going to be no good sigma complex. You just pick the lesser of two evils. Right? So let's look at, so I'm going to draw out, I'm not going to draw them all out, because I think we can do this. I'm going to draw out the bad ones. Right? I'm going to draw the bad one, and then maybe the not the worst one. Right? So the bad one for this, if I go ortho, the bad one is
Thank you.
the bad one is, oops, let me slow down here. If we have the aldehyde, where's the worst place to put the plus charge?
Right
Next to the aldehyde, right? That's bad, right? Plus charge, delta plus. So we don't want the plus charge there. And that happens when the electrophile is there, right? In the ortho position. You get, one of your sigma complexes will look like this. This is just one of them. And this is the worst one, right? So you see this, you say, well, this is bad. Well, that makes sense because we knew it wasn't going to happen anyways, right? Because of the initial resonance structures. But I want you to make this clear distinction. There's resonance structures of the starting material that you can draw and garner this information. But then when you actually do the reaction, right, when you actually just do the reaction, you can look at your sigma complexes and say, well, hey, I'm not going to make a very stable intermediate. That's also why this isn't going to happen. Remember we talked about reactions take place for one of two reasons, or two or both reasons, right? Reactive starting materials or stable products or intermediates. So this is a twofer, right? This is not making the starting materials more reactive, and we see that for resonance structures. Starting materials are not more reactive. And heck, the intermediates are also not that stable.
Just bad.
Just bad. So let's do the para one.
These are all the worst ones that you're drawing?
I'm drawing the bad ones.
Okay.
So electrophile's here. Make sure I do this right. Yep, there'd be a plus charge here. Make sure, did you guys all get these kind of sigma complexes on this side of the room?
Yep.
You didn't get one like this from the para? Didn't?
I did.
You should have. You should have. You should have. Double check. And again, why is this one bad?
Because it's so close to...
Plus by the plus, right? So I'm assuming you can draw these out. I'm just giving you the bad ones here. So what about meta? So ortho and para have bad ones. Meta doesn't have any bad ones, but doesn't have any good ones. But that makes sense because, again, is this an activator or deactivator? Deactivator. So what's it going to look like? There's an E, there's a plus, here and here. Right? So this isn't particularly good, but at least it's not bad. Right? So we could say bad, bad, not good. But not bad. Right? Not good, but not bad. Okay? Let's go over here.
Oh, Lordy.
So the good sigma complexes
There's
over
no way I
here
can record this.
are the best ones.
Should I slide up there?
You're going to have
So you can see it.
No, I mean the screen is so small. You'll see it on the computer. Hopefully.
in the electrophile's ortho. Right? You're going to have, this is the fourth, here it is. This is the mysterious fourth sigma complex. And it's also the best sigma complex. And why is it the best sigma complex?
Octet.
This is the best, and it's best because everybody's got a full octet, right? Octet. Yay. So this also proves, or gives us evidence, right? Just like looking at the resonance structures initially, looking at the intermediates, right? Seeing that we can make a fourth intermediate, which has full octets, that also leads credence and says, yeah, ortho is a good idea with this activating group. Yeah.
So in this case, it'd be better to have a complete octet than to have resonance. Is that correct?
Having it is part of this is still resonance. This is still
okay.
sigma, right? Sigma complexes are a particular type of resonance structure.
Mm.
So it's still resonant. So it's even better. It's a fourth resonance structure, a fourth sigma complex. So still good. What about para? Same idea. Electrophiles here. Be pi bonds here. So again, right? This is great. Full octets. Right? This makes sense. We did the resonance structure of the starting materials, and that told us ortho and para directing. Now we have two good sigma complexes for when that happens. Right? So this is kind of like the egg, right? What came first, right? We have evidence on both ends. Starting materials are more reactive, and we know where they're more reactive. And we have intermediates that are more stable, and we know why they're more stable, right? For different positions that get reactive. Yes?
Yeah, it is.
So meta, there's not that there's anything, this is like, there's nothing bad about meta, but there's nothing good, right? So why would you choose to go meta? If you're an activator, why would you choose to put the electrophile meta when you have these better options? Would you? No. Unless, lab this next week. Unless, what else could be a factor, right? So what is this all about? So this is, now you get to find out the dirty secret of organic chemistry. You can answer any question with two things, essentially. You can justify any answer, any principle with two things. So what are we talking about here? What are we moving around here? We're moving, not moving, what do we move? We don't move the charge, we move electrons. So you can say, well, this is an electronic effect, right? This makes sense. So we talk about this, we're talking about electronics. We're talking about moving electrons. What's the other kind of effect you think that's out there that we can argue? So remember I told you, how do you decide between ortho and para? What could be a factor between deciding if you get more of the ortho product or the para product, right? Because both are good. So how would you differentiate between them? So size. So either it's electronics that's the principle, that's most important, or it's sterics. So it's either sterics or electronics. So you'll find out in lab next week how big a role sterics can actually play. And maybe to the point where you think you should get an ortho or para product, but guess what you get? Meta. What?
What's an example that an activator would stare to?
Depends how, just have a really big electrophile. Have a really big electrophile, right? So if your electrophile is really big, or if your activator is really big, right? That's pretty bulky. If you put a bunch of stuff for, make it huge. Let's put a bunch of carbon. I'm blocking these ortho spots. There's a bunch of junk in the way.
But wouldn't para be a better?
So then it would go para. Then the electrophile will add para. Exactly.
What's this big carbon chain?
If there's always something at para, then maybe nothing's going to happen.
So if there was like another side chain on the meta, then the other meta would be a better.
Sure. This is already getting a little more complicated, right? Getting this? Get this idea? Okay. Let's see. So I haven't. So if you pull out class notes for today, so I didn't quite get a chance to finish
Electronics.
chapter 19.
Determine where it goes.
We have one of two options.
Stairs is like size.
I like physical shape.
The biggest thing you need to know to be able to do the rest of chapter 19, actually we have time to do it, it's really simple. So look at the back of your class notes, number 2. Right, I'm not asking you to know the mechanism for this, right? But you can take aniline. And react it with NaNO2 with HCl. And what you get is something called a diazonium salt. You get that. So if you look at that, what does that look like to you? So we're going to do a substitution here. We're going to substitute this out. Why do you think it's easy to substitute this group out? What does that look like to you? What is it? Well, it's a good, right? It's a good group to leave, but if it does leave, what is that group?
It's just
Yeah.
N2, which is, and what is N2?
gas.
Right? How do you shift equilibrium? One of your reagents, just one of your products is a gas and goes away. Guess what? It's not coming back unless you're under pressure. So we make this, right? So it's a nice way to take, and right, this could be NH2. Let's say we want to get rid of it. We could turn it into this diazonium salt, and then essentially, if you look at your class notes, and I'm not going to require you to memorize all of these, but basically, if you want to switch this with chlorine, what would you add? So write down number here. There's 6 things. If you want to switch out with chlorine, what would you add? Cl minus. If you wanted to switch that with fluorine, what would you add?
Fluorine.
F minus. If you wanted to switch that with iodine, what would you add? Bromine? Yep. What if you want an OH? What do you want to turn into phenol? What would you add? OH minus or water. And then the last one, if you just wanted, what if you just want to get rid of it and make it an H?
H2.
It's actually, it's like an H minus. Now, this is acceptable to me. The actual reagents are a little more complicated, right? So in sapling, go to the back of chapter 19. Like, I think this is HBF4. This is maybe HI, this is HCl. So there's some different, more complicated. Like H minus is actually H3O plus. Right? OH minus, there's actually 2 ways to do it. Actually, no, this one is H3PO4. H3PO4. It's a phosphate acid. Phosphoric acid. But the point is, right, all I want you, right, this is a slick way to change out this. And this will help you finish your final homework. This is the last little bit. But you don't need to know the mechanism here. I'm not asking you to know the mechanism. And it's as simple as once you got this, then we're just doing substitutions, right? We're just substituting the N2 for all these different things. But look in the back of the book for the specific reagents when you see those that's happening. Okay? Make sense? Good.